now that we've learned all the different ways that we can graph quadratics, we're going to talk a little bit about the different characteristics and how we describe a quadratic function. So let's get right to it. So in lesson 3b7, we're going to be talking about characteristics of quadratic functions. So our learning target is I can identify and interpret characteristics of a quadratic function. I am going to split this into several different videos because characteristics of linear functions in Unit 2 was something that I saw a lot of students struggling with. So I'm going to try and break this up and kind of go over it a bit slower to hopefully clear up any of those misconceptions that are holding over from Unit 2 and make sure we understand how these characteristics apply to quadratic functions. So some of the things that we're going to talk about with quadratics we've already discussed. The first one is the line of symmetry. A line of symmetry is a line that divides a parabola into two equal halves that are reflections of each other. We've used this already to help us graph things, so this isn't anything new. We also have the vertex, which is the maximum or minimum value of a parabola. We've used this before when we were graphing them. Then we have a maximum or minimum value of a function in a specified neighborhood. That is basically just another word for vertex. It's the extrema is what we call it. But there are some situations where extrema and vertex are not exactly the same thing, and I'll show you what I mean by that when we start looking at some graphs. The highest point or peak of a function is going to be the maximum, and the lowest point is the minimum. We also have the word roots. And roots, again, we've used that word kind of throughout our conversations about quadratics. Root is just another way of saying x-intercepts, zeros. These are all words that can mean the exact same thing. It's just the place where your graph is crossing the x-axis. So you've got to be prepared when you're taking a test or a mastery check or anything like that to see the word roots or x-intercepts or zeros and know that they're really all the exact same thing. Right, so let's go ahead and, we got a couple more things I want to talk about. The place where a function crosses the y-axis is simply known as the y-intercept. All of our possible x values of a function or inputs is the domain. This is something we've seen over and over again. And all the possible outputs of a function are the range. So go ahead and pause and get all those words copied down if you haven't already. They should also be in your glossary. So what we're going to do is I've got two examples, two very different parabolas here, and I'm just going to talk about all of these sort of fundamental characteristics in relation to this example 1 and example 2. And then we'll look at some of the other things that other characteristics in a separate video. So AOS just stands for axis of symmetry. When you're trying to find the axis of symmetry, what you're looking for is a vertical line that divides this parabola perfectly in half so that either side is a mirror image of the other. You are going to report your axis of symmetry as an equation. So this is going to be the equation x equals -1. I know that it's x because it's a vertical line, and that's always x equals a number. Also because all of my x values here are equal to -1. I know it's -1 because this is -2 and this is 0, so it's halfway between those two. Okay? The vertex is going to have the same x value as your axis of symmetry, so that makes the start of my vertex easy. The y value, I'm just looking at where is the very bottom of this function. So that's at -1, -4. And you're going to report the vertex as an ordered pair. When we say max or min, basically we just want to know, does this parabola have a maximum or does it have a minimum? Because it's opening upwards like that, the vertex serves as a lowest point, so its extrema is a minimum, not a maximum. Now my roots are going to be the places where I'm crossing that x-axis. So it's going to be right here and right here. You should report both of those as an ordered pair. So the ordered pair here is -3. Again, we've already figured out that this is counting like every other line is 1. So that's -1/2, that's -1, -1.5, -2. So this is going to be -3, 0. And this one is going to be +1, 0. My y-intercept is the place where I'm crossing the y-axis, which is right here. That is going to be, I haven't gone side to side at all, so I've got an x value of 0. My y value is -3. Your y-intercept won't always match up with one of your x-intercepts. It just happens to be that way this time. Now, for a quadratic function, your domain, remember that just because there's not an arrow here, if it's going to the edge of a graph and there's no indication that it stops, you can usually assume that there should be arrows there. So my domain here, we can assume that this is going to continue to go to the left forever. To find domain, you look for the smallest possible x value. So I'm going to make myself a little line here. So you can take your pencil and kind of turn it to the side and drag it along, and the first place you see an x value is going to be the first value right down. Well, the first place I see an x value is right here, except there's an arrow attached to it. So that means that when I write this down, I'm going to have x is less than, right here, I'm going to put my smallest possible x here. Because there's an arrow attached there, my smallest possible x is -infinity, because it's going to keep going to the left and getting smaller and smaller forever. Then for the value that goes here, I need the largest possible x. So I keep dragging it till I get to the end. Well, it's at the end right here, but again I see an arrow, which means it's going to continue to rise up forever. So my largest possible x value is +infinity. I'm going to do the same basic thing for range, except for range, I want the smallest possible y value and the largest possible y value. So now I'm turning my pencil side to side, and my range, I'm going to have y is less than and less than. Here I'm going to record the smallest possible y value, and here I'm going to record the highest possible y value. Well, my smallest possible y value, the first time my pencil hits this function is right here at -4. So the minimum here is -4. Notice that that is the y value of the vertex. That is not a coincidence here. The highest possible y value, when I go to the top, it looks like maybe it's 2 there, except I've got arrows, which means my highest possible y value is going to be +infinity, because it's going to continue to go up and climb forever and ever. All right, so, well, let's look at an example that's slightly different. We're going to start again with our axis of symmetry. So axis of symmetry is the same as it was before. I'm looking for that point that cuts it in half. You're usually going to go right there to your vertex and then just drop yourself a vertical line. It is going to be x equals something. In this case, it's x equals 2, because my x value is 2 there. My vertex is going to have an x value of 2. It is this point right here where it peaks and starts falling. So that is 2 and then up 2, because my y value is 2 as well. All right. In this case, because this thing is opening downwards, this is a maximum, not a minimum. So I'm just checking that off. Now I'm looking at my roots. My roots, remember, are my x-intercepts. So I'm going to write that down for those people who refuse to turn the volume on. My roots are my x-intercepts. So I'm going right here and I'm going right here. This first one, this is 1. That looks like it's at about 1/2. Maybe not exactly, but if it's not perfect with graphs, it is going to be sort of an estimation. So we'll say 1/2, 0. The y value of a root is always going to be 0 because you're not going up or down at all. And then here it's about 3.5. So we're going to say, I'll just put 3.5 because that's easier. And then my y value is 0 because it's not going up or down at all. Right, the y-intercept is right here. So that I didn't go side to side at all. So my x value is 0. I'm going down to -2. So that's my y-intercept. All right, now I'm ready for my domain. Again, remember that if it goes to the edges and there's no indication that it should stop, then you can assume that there are arrows. So let's go ahead and take my little makeshift pencil here. And remember, domain is going to be left to right. You are going to have an x, and you want the smallest possible x and the largest possible x. Well, in this case, the smallest possible x looks like it's right there a little before 0, except there's an arrow, so the smallest possible is negative infinity. And then I'm going to keep going over till I get to the very end. And the highest possible looks like it's a little bit after 4, except again, I have an arrow, which means positive infinity. Here's a hint for you. If it's a quadratic function, your domain is always going to be negative infinity to positive infinity, which means all real numbers, which means you could see it written out, all real numbers. Because unless it's a word problem that specifically tells you that you can't go beyond a certain amount or below a certain amount, you can assume that you can plug any value you want into this, which means your domain is all real numbers. The range, though, is a different story. So to find my range, I need to turn this to the side. And now I'm going to look for my y values. So again, I'm going to go ahead and write this in. I'm looking for the lowest possible y and then the highest possible y. My lowest possible y here looks like it's right there, except again, I've got those arrows, which means my lowest possible is negative infinity. I'm going to go up to the top of this guy, and the highest possible y value is positive 2. Now, one thing I forgot to mention in the previous example, and we'll go back and talk about it, is this function actually hits a value of 2, which means you should add the little equal to here. It doesn't ever get to infinity, so that's just going to stay as a less than. I don't have to put the equal to. But when you get a max or a min, most of the time it's going to actually hit that value, which means you can say equal to. So over here, when my range hit that -4, I'm going to say, oh, it's actually equal to -4. So I'm going to put that underneath that equal, or that less than. Again, notice that the range goes up to 2, which is the y value of the vertex. So you are going to end up using some of the same numbers over and over again. Okay, I'm going to pause this video now and let you get some practice with these particular characteristics, and then we will move into talking about some other characteristics. So I'll see you in a minute.